Okay, now we're going to start with our panel review on the surface water hydrology and climate meteorology. I should say that we did have a panelist lined up who was an expert in climatology, meteorology, and surface water hydrology, especially in northern climates. And unfortunately, kind of late in the game, he had a conflict and he had to cancel out. And we tried very hard to get a replacement for him. Unfortunately, we were unable to. But fortunately, several of our already existing panel members have some expertise in some of these areas, and they offered to help out. So I think we're in pretty good shape, and I'd like to go ahead and start with the introductions. I'll start at this end. Next to Brad is Tom Myers. Dr. Myers is a researcher and consultant in hydrogeology and water resources. He has a BS in civil engineering from the University of Colorado, MS and PhD degrees in hydrology and hydrogeology from the University of Nevada at Reno. He specializes in groundwater modeling, hydrogeology, environmental forensics, regulatory compliance, water rights, NEPA analysis, and environmental and water policy. Next to Tom is Dr. Katie Walton-Day from the USGS. She's a research hydrologist and water quality specialist for the Colorado Water Science Center in Denver. She has a bachelor's in geology from Smith College, MS and PhD from the Colorado School of Mines in geology with a minor in geochemistry, and has been working for the USGS since 1984. Her primary research areas have been the hydrologic and geochemical processes affecting metal mobility in wetland streams and groundwaters that are affected by acid mine drainage.
And then we have two panel members who served on the first panel with us. We wanted to build in continuity between panels, and also with Water Rock Interaction, having people who sat through the and reviewed parts of the more solid phase geology and on the hydrology and water chemistry was going to be important. So next to Katie Walton-Day, we have Chris Way-Thomas, who we've already introduced twice, but for the third time. He's a research scientist with the USGS's Volcanic Hazards Program. He's centered here in Anchorage with the Alaska Volcano Observatory. And yeah, he's with the USGS, background in geomorphology, hydrology, and quaternary geology. And then on the end is Dr. Tom Al, professor in the Department of Earth Sciences at the University of New Brunswick, has a PhD from Waterloo in 1996, and he's our geochemist with expertise in geochemical and hydrologic studies of mine tailings and waste rock and the release of inorganic constituents to groundwater. Who would like to start on with comments here? Either side is.
I'll go ahead and start. We'll go this way.
All right. Thanks, Tom.
Okay. Well, I'll start off just with a couple of basic questions about about those meteorological sites. You did not collect any solar radiation data. Is that correct?
No, we do collect solar radiation data. Didn't present it. Typically with the more lay audience, the temperatures, winds, and precipitation tends to be the focus. But all of these stations do collect solar radiation, barometric pressure. The temperatures that are collected are also done at multiple heights to assess vertical differences in temperatures.
Okay, I mean, I'm asking that question, then of course, I mean, tomorrow's discussion will be getting into potential evapotranspiration, and it sounds like you may have collected the data for PET yet, and I'll ask this tomorrow, but because it wasn't used in the water balance, that's why I was asking that. That's why I wanted to ask that question. You've also mentioned that the rain gauges or the gauges have a very, very low catch efficiency. Have you done anything to estimate what that efficiency is? I mean, do you have any references that would suggest, what it is? And I also, and the wind speed's very high, which of course leads to the low catch efficiency, but I also know, I mean, there's sort of an axiom in the Sierra Nevada mountains that when the precipitation starts, the winds drop off some, not a lot, but they drop off, and therefore the average may be a little high. The average that you reported may be higher than the average that occurs during the biggest storms event. So you may not be, the efficiency may not be as bad as you're thinking. And I'm just wondering if you have any thoughts on that.
Well, one of the limitations that we've had, there are a number of studies primarily geared towards assessing the variation between different types of wind screens and how efficient they operate that have been done on Arctic and subarctic climates. Dr. Yang, as well as Wagner, have presented a number of papers documenting those. Almost all of the papers start to fall down when you see the type of wind speeds that we see at the pebble and the deposit area. They don't go beyond that because there's not as many places that they've studied that have that high level of winds. So, but that being said, you can extrapolate those findings out, and within those papers, there's a relative degree of confidence as far as you could develop correction factors and algorithms based on those papers to then apply to the data to back calculate it. So in some cases, your efficiency may be 70%, and that's predictable based on the design of your wind gauge and so on, and then you can check that and apply that correction factor. Throughout the history of our measurements, and Jamie might be able to talk more about this, is we have compared the stream flow data in that general area to the precipitation data, and when you apply those correction factors, they corroborate each other quite nicely.
Pass it down to you, Katie.
I had some more questions for Jamie on surface water. I think the reference that you used for the peak flow regressions, USGS reference, we were just John Osman, who runs our gauges there, is here in the audience, and he mentioned that there's a new reference of regression equations.
Right.
Are you aware of that?
Yeah.
Okay.
We had used the older one.
Sure,
and
sure, 'cause
carried
that's all
through.
that was
That was
available.
available,
Right.
but we were definitely going to use the latest and greatest as we move forward.
And then I wondered if any thought had been given, because of the limited period of record and the limited gauges all over the region, if any thought had been given to doing some paleo flood analysis to try and extend the period or the peak flows. There are people around who do that.
Yeah.
And I don't know if you guys had given any thought to that, because I think it might be really helpful, but I don't know in your physiography if it's a viable thing.
Yeah. Well, we haven't actually. That's something we can look into for sure. We haven't done that yet.
Mm-hmm.
I'm aware of that kind of study, and the streams that we were looking at didn't seem to lend themselves that well to it.
Okay.
But it doesn't mean we can't explore that.
Sure.
Sure.
I mean, maybe for the audience, could you explain why it's important to understand the peak flows?
Sure.
What that would be used for?
Yeah, I mean, there's a number of different factors. I mean, if you're looking at fishery studies, for instance, they look at the mean annual peak flow is an important channel-forming flow, so from a geomorphological perspective, and we want to get an idea of that. So if we're implementing some sort of mine that's going to change that, how would that affect the stream? And then again, what turn would that effect have on fishery, etc. But from an engineering perspective, if we're designing any sort of diversion structure or something like that, we need to know a much larger return period event. So most of the diversions would probably be designed for like a 200-year event, something in that order. So we need to get a handle on that. If we're looking at a tailings dam, we're dealing with a much larger event, something like a probable maximum flood, in which case then we'd be using a modeling exercise to take what they call the probable maximum precipitation, and I'm not going to get into the details with that, but that's something that, the largest conceivable precipitation event ever sort of thing, combined with snowmelt. And it would be a very large snowpack combined with that, and then you model it as a flood, and then you'd have to design your structure to handle that event, with the idea that that event is so large it conceivably cannot occur. I mean, that's really how it works. So that those are all peak flows, but the peak flows that we were looking at there were based on the historical record, and it's typically involves something called the frequency analysis, which again I won't get into the details of, but there we have a very short database. We were only discussing 5 years. We've now got an additional 4 years of record, and again, that sort of typically you can take the record that you've got and sort of double it. So if we have 10 years of record, we can get a pretty good idea of what a 20-year flow event is, a peak flow event or something to that. If we're dealing with a 100-year event, then we have to start looking at different factors, different ways of using it, using the longer-term regional information and that kind of stuff, which is, again, what those USGS regression equations are trying to predict as well. Their accuracy is going to be better in the shorter return period than they are in the longer return period. Again, the other thing is estimation. There's a lot of estimation involved in doing that, and you can build in some factors of safety, if you want to call it that, fudge factors. So if we know that there's an error band around our 100-year estimate, well, we'll take the upper band, and that provides us additional comfort level when we're doing the engineering design, that sort of stuff. So,
Okay,
yeah.
thanks. I also had some questions about the losing reach in the South Fork. And I greatly appreciate the difficulty of those low flow measurements. But on the map, there was a yellow no flow line drawn between 3 pretty far spaced stations.
Right.
Did you actually take measurements, not take measurements, but drill through the ice and snow between those stations to see if it was no flow, or is that I know that was kind of the flyover, and so the fact that it was iced over was saying there was no flow, but do you infer from that there was no under ice flow?
Yeah, if the measurements are taken in between those points, and then based on the hydrogeology model and also the groundwater table measurements, you have a pretty good idea if the groundwater table has dropped well below the surface at that point, that the groundwater is not resurfacing in between, because it's fairly well mapped out there with the surficial geology that's a massive gravel deposit.
Okay.
So it would be very unexpected to see it surfacing. I mean, there's no guarantee that it doesn't in little places, but as our understanding of the hydrogeology and the surficial, the surficial geology, the hydrogeology, and then our understanding of the hydrology, we wouldn't expect to see flow there
Okay.
at that time. Yeah.
Thanks.
I'm going to follow up on that if you don't mind. Just thank you. You have groundwater measurements so that when the reach is flowing, the groundwater level is is as high as the bottom of the channel, whereas it drops below. Are you saying it drops below the channel only when it is dry? So it's not. So it's like during the summer freshet runoff period. It's not that it's just a losing reach, but still flowing. So
Right.
So are you saying that the groundwater table does rise to the bottom of the channel during the freshet?
I'll actually
Or maybe you're not the right person.
Yeah, I'm not the right person, but I'll ask. They are in this room if you want to. I don't know if we have.
Well, it's more of a conversation for tomorrow, but
Yeah,
you just said that
No,
you were
well-
relying on the groundwater level, which is why I jumped in there.
But I have spoken with them about that, and they have told me that the groundwater drops quite dramatically there. So it's more than 15 feet below the surface during the wintertime. The groundwater table does fall and rise dramatically there, and they know it's well below the surface at that point. And given how slow the flow is at that time of year, even if we do have flow in it, it's unlikely that it's perched up that high above the groundwater table with such little flow in the creek.
And we can revisit that tomorrow, too.
We
Yeah.
probably will.
Yeah.
Okay, I have a number of questions I'd like to ask. The USGS equations that you're referring to, those pretty much come from the Jones and Fail work.
Yeah.
Could you describe how you arrive at those, how those equations are constructed?
Sure. Essentially, they take, again, the data set there, as you understand, is very limited. So they've taken whatever historical flow records they've got, peak flows, and then they've taken various other parameters, such as precipitation that they estimate for the particular site where they've got flow. They take how much lake area there might be, other factors, maybe glacier. There's a whole series of factors, and then they do a regression between those factors and the flows that they're getting. And they come up with a series of equations that relate, okay, if I have a drainage with this much area and a mean annual precipitation of this and this much lake area and this sort of thing, the equation predicts this is what the peak flow would be. So that's essentially how it goes. So they're a first guess, an estimate, because they work quite well if you've got a very extensive database to work with. If you've got a very limited database, which is what you have in Alaska, then there's going to be a lot of uncertainty around those peak flow estimates.
So when you use these equations, did you develop them for the basins that you were working in, or did you just use the regional?
We use the equations as they provide them. They've got different hydrologic zones.
Right.
Okay, but we look into and figure out for the drainage that we're looking at, what is all those parameters. So what is the drainage area of this? What is the...
Right. So you got your own basin characteristics.
We have our own basin characteristics that we plug into those equations, and that produces the flow estimate, and then we compare that to what we've actually measured in that basin. And that's where, I mean, again, it was done with only 5 years of data, but that gives us some idea whether those equations tend to underestimate or overestimate the peak flow, low flow, et cetera.
What are your thoughts on that approach? Do you think that's using the regional regression equations?
Right.
Do you think that's a legitimate way to do this?
Well, I would say it's not on its own. We use it as a first estimate if we've got nothing else to go on. I'm much more comfortable using site-specific information, of course. And then as our database progresses, we're going to be able to refine those estimates all the time. The other thing is that we've looked now at, because we've changed our precip estimates from what they were back in 2000 when we did the EBD. We've refined our watershed model, and part of that is refining the precipitation estimates, and that will then changes our peak flow estimates as they go through in the U.S. regression equations. And as a result, those numbers are actually closer to what we're measuring now. So it looks like those equations aren't actually that bad. Right. But typically, a lot of times you use them without any sort of calibration. But what we're doing is collecting data at site so we can check them. Right. It's a starting point, but it's not the end-all be-all. Yeah.
So if you work with the Jones and Fail report, you know there's lots of data in there.
Yes.
So one thing you could do is you could take the drainage basin area peak discharge data and plot that up for that region and draw an envelope curve which should indicate what the largest possible or at least measured flows are going to be, and use that as somewhat of a guide for the peak.
Yes, but again, recognizing the periods of record on there are even that they use were not that long.
They're not.
So we're when I'm looking at a 100-year event, I would very much expect it to be outside of that. Having said that, the Iliamna River had a massive event on it, right? And if you look at the data set from there, I think the data set's like 13 years or something. But the largest event on there is 2.5 times the second largest event on there. And so that gives us some idea. But if that event itself is probably in the order of a 100-year event or something like that. Right. So we look at all the information. We're not just, like, I actually am not a big fan of regression equations myself. I'd much rather look at the available regional information.
I don't like them either. But.
No, so we just use them as one sort of line to sort of compare against. But I'm not putting a lot of weight on the estimates that come out of it.
Kind of a fruit cocktail of parameters.
I'm much happier looking at historical flow patterns and looking at the statistics, the actual statistics in the distributions of the data. So looking at the skewness and the standard deviation or the coefficient of variation and the means of the peaks and that sort of stuff, and looking at all those stats and seeing how they scale on a regional basis, which is what you're talking about, drainage area versus that, and using all those and then fitting those into a distribution. So that's actually what my entire PhD was on. So if you want to get into that, we can talk for
all right,
we can
good.
talk
We're
for
talking
hours.
The same language. But I just reiterate what Katie said about paleo flood indicators, because that's really going to tell you what the largest events have been in the region, and establish an upper bound, which is a good check on whatever you use for the PMF PMP approach.
Right.
Because in order to know whether that's realistic, you got to have some evidence that there were even floods that large. Right? So if you want to know, let's say, what the 500-year event was, you got to have some benchmark in the area that you can calibrate that to.
Yeah, you also have to recognize what's driving those things, though, because I mean, if you're looking at something and it was due to some sort of glacial outflow event or something like that,
that's right.
That's pretty darn hard to put like.
Right. Yeah, it's a different animal.
It's a totally different animal. Yeah. So, and also just knowing even the way we estimate peak events now in terms of, okay, we've got a high water mark and we're going to use the slope area method or Manning's equation or whatever to do it. There's a huge uncertainty in that. And then you now extrapolate that to the paleo type thing. The error bands are.
Yeah.
So it all has to be taken in proper context when you're looking at that, but we can certainly do that.
But I believe that stretch of the New Halen is in bedrock, right? So
it is.
You have a pretty stable cross section.
But it has a massive lake upstream of it. So the New Halen, if you actually take a frequency analysis of the New Haven data and you do it for the Iliamna River, you get a higher 200-year event on the Iliamna than you do on the New Haven,
Exactly.
even though the New Haven's drainage area is massive compared because of the effect of the lake and everything else.
That's right.
So, and also the effect that one large event has on the skewness of the data set. So, and we're getting into details that most people don't understand. Well, anyway, yeah.
Well, so
Chris,
another
Chris, can you-
question.
Chris, can you just, for the audience, say what you're referring to on the paleo events, that you're looking at a sedimentary record versus?
Yeah, so when a river goes into flood stage, it's going to leave behind a flood deposit along the channel somewhere. And if you can locate these deposits and date them, you can get some sense for what the largest flows may have been. So the maximum evident flood in a drainage basin is something that's worth knowing about. So it's what's the biggest thing nature has done in this basin? If you can figure that out and figure out when it occurred, that's valuable to know, because it's a good check on any theoretical calculation you might do by importing a storm from someplace and having it fall on the drainage basin. So you got to have some physical evidence somewhere what the biggest floods may have been in the past.
Right.
So,
Thanks.
Paleohydrology is a very interesting, something I did quite a bit of when I was a postdoc. So, okay, next question has to do with breakup conditions.
Right.
And as many people in the room know, in the spring we have a serious ice jam flood issue in Alaska. And so I'm just curious what your understanding of breakup conditions are, and do ice jam floods develop on any of these drainages, and if so, what are the implications for hazards and stuff like
Right. There definitely is the potential for some. They're fairly low gradient streams though, so we don't get like a narrowing where you get a big jam and a big buildup of water behind it, so the reservoir, and then a burst flood type of event. You typically get an ice and it just overflows the banks, and then you get localized flooding all around. So particularly in the lower reaches of all those streams, you see lots of overbank flooding during the spring because we've got little jams here, there, and everywhere. It makes it extremely difficult, of course, then to measure the flows under those conditions.
Right.
So, admittedly, the peak flows that we've measured, sometimes, we have to discount the measurements because we really don't know what's going on at certain points. We try and take that into account when we're coming up with the annual peaks. Is this, like when you review the stage record, is this real or not? I mean, what was going on that caused that kind of thing? So it isn't, because you can look at those episodic events and say, oh, like that's going to produce a much larger flow than a traditional sort of frequency analysis might predict. Because if you get an ice jam and then you get sort of a flood burst type of event, you can get a much larger event, and it might come at a much more frequent time period than what you might expect. So we definitely consider that. I mean, it all depends on the application. If we're just building a little diversion ditch or something, then that's probably not a big consideration, right? If you're building a structure across the river, downstream of something, then that is something that you might want to consider.
Right.
So that comes into the engineering and the understanding of what these peak flows, how they're derived, and what are they applied to. So,
That's right.
yeah.
that? Since a number of these streams are low gradient and shallow, are there icing conditions that develop? Alpha ice generated?
Yeah, absolutely. And so again, our winter flow measurements are, the USGS has positioned their gauges when Pebble asked them to put gauges in on each one of the streams. They didn't specify where. They just said, find the best location that you can try and get an annual type of hydrograph from. And I know because we've seen changes to the information that they've published in the winter after they've reviewed it and changed it and that sort of thing. So they do try to account for the ice effects, which is a pretty standard thing in northern climates. Yeah.
And then just one last kind of general question. Any other hydrologic hazards to be concerned about? Thinking of landslide dams or anything like that?
Not on the road corridor, yes, or transportation corridor.
Right.
Not in the mine study
I
area.
didn't think so.
I mean, the slopes are a little gradient. There's been a lot of glacial activity in the past, so they're very, very smooth hills. there's no real landslide activity evident anywhere around the mine study area. But definitely as you go on the corridor, the transportation corridor, though, there have to be something considered. And that goes to sort of this episodic event type of thing again. Would you have some sort of debris flow blockage and then flood event that would far exceed a hydrologic event in terms of trying to determine what would be the biggest flow we should design this bridge crossing for, that type of thing? Yeah.
That's right.
Yeah.
Yeah, that's all I have.
Okay.
Okay, so I've got a couple of questions. One relates to the rating curves. So you showed one rating curve, and I'm wondering, is that characteristic of the others in terms of the number of data points and a range of stage variation and so on?
Yeah, that rating curve, it was shown really, it's quite a good rating curve as they go, just as a demonstration. We have a number of others that shift. So we've actually had multiple curves and had to reestablish a new curve each year, that kind of thing. The USGS has as well at their sites. They have generously shared the rating curves with us, so we know what they have at their sites as well. And in those cases, you know, the typical guideline is you need a minimum of about 10 well-spaced points across the range of stage that you typically measure, that kind of thing. So we're making an effort to do that. I mean, we've been visiting the sites they were for every single month sort of thing on regular at all these different locations. And then as needed. So if we have a site that's more problematic than others, you might have to visit it more often, reestablish new curves.
Okay.
Typically, the biggest events, of course, come in the spring. So shortly after you check, take a few measurements. Do they fall on the curve? Oh, no, they don't. They're off. That means we're going to establish a new curve. It's the same routine everywhere. Yeah.
A lot of work.
So.
Okay, so then the extremes of those rating curves is also of interest. You talked a little bit about recurrence intervals and challenges in extrapolation and so on.
Yes.
So if your rating curves are shifting, then you're going to have a lot of problems with, you know, going beyond the period of record, right?
That's right.
So,
Yeah. I mean, what we typically when we're doing the extrapolation is based on the flow record that we have, and then extrapolating. Say we've got 10 years of record, we're trying to use that to fit a distribution and then predict a 100-year event or something like that. There's the extrapolation of the rating curve itself, and then often the stage that's measured is higher than the highest point that you've got for your rating curve. So there's that extrapolation.
Right.
So there are techniques to extrapolate, and then, but of course there's uncertainty with that. So as with any hydrologic program, the best you can typically measure a discharge is in the order of plus or minus 5% under ideal conditions. So, you know, as the conditions get trickier, as under very high flows or under the ice or whatever, that error band increases. But that's common to all hydrology data, including...
Oh, sure, yeah.
Yeah, so...
Well, I guess I'm exploring it also because I'm interested at the low flow end because your low flow data is informing the groundwater model too,
yes,
right?
Very much.
And you talked about measuring low flows. I'm not sure where all those measurements are coming from. Are they the green dots that you showed where you're going in and making a point measurement?
Yeah, well, there's all our stations that we visit regularly. So we have those. The USGS maintains their gauges through the winter, so they have some pretty good idea what's going on in the wintertime. Generally speaking, we don't get a lot of warming periods where we suddenly see a lot of melt happening. So the base flows are fairly steady throughout the wintertime, and you get this sort of receding, the recession curve. So that helps us sort of connect the dots. We were going in monthly in the wintertime and taking point measurements, and at all the stations, and then in March there'd be a low flow visit, an additional 26 stations, so at different points, because that tended to be the lowest flow period just before breakup, and that's what we were most interested in, was how low did the flows get, and that helps to guide, because at that point it's a recession, it's gone down to as low as it's all being fed by groundwater, the groundwater's receded throughout the wintertime, and that helps us in terms of calibration of the groundwater model too.
So in terms of low flow numbers and interaction with the groundwater flow model, those low flow numbers are not necessarily coming right off your rating curve.
No, they're not coming off the rating curve at all, because we know the rating curves are useless in the wintertime because all the snow and ice and everything.
Yep.
So we actually take most of the stations out in the winter. We're not measuring water level at all.
Okay.
We're just taking a point measurement at different times and then more or less connecting the dot and assuming this. And then we're looking at that and comparing it to the USGS and saying, okay, they've been measuring. We know that they're having to make their own adjustments for the ice effects and whatever. what does their recession curve look like, and how does ours compare to that? And on this date, when we measured this, what did they measure at theirs, and how do those compare, and that kind of thing.
Good. Okay.
Yeah.
No, that's a lot more clear. I'm also interested in this. So you showed the unit runoffs for the three.
The main stems,
yeah.
of the 3 tree.
And the Upper Tulare Creek one in the spring is about 50% of the other two.
Yeah, it's a lot lower.
And you attribute that to recharge, right? But you don't see it in the fall.
You
Yet
don't.
you've got a long recession period between spring and fall as well,
yeah.
right? So
Well, some of it, it actually, if you notice, it doesn't come down nearly as low in the summer, generally, as it does in the winter time. And then what the actual wettest periods tend to be in, the 2 wettest months are August and September. And in those periods, you'll see all 3 of the things very similar.
they behave the same.
Yeah, I mean, we attribute a lot of it to the groundwater, because then when it gets going into the winter, the other 2 drop lower. Upper Tulare stays high. It seems to have this greater storage of water and then release, but it also has lower precipitation, so it tends to have a smaller snowpack. It appears, working backwards from what we've had to do in terms of calibrating our model.
That's the first thing I looked at, though. It doesn't seem, it's not a big difference in precipitation, though, is it?
No.
Is there certainty in those measurements to begin with?
No, again, I mean, what we've, as Brad alluded to, winter precipitation measurements are highly uncertain because of the catch efficiencies. And so what we've done is tried to work backwards, and again, it's kind of in that, okay, we have fairly high confidence in the streamflow measurements because we've got 34 stations and they're all telling us the same story. That helps to sort of, and 3 of them are operated by the USGS, completely independent of us, so as long as, if there's consistency all the way through, that tells a pretty strong story. What precip do we need to get to give us those flows is kind of how we've had to work backwards, given the general patterns that we have at Iliamna, knowing the temperature patterns and all the rest of it, and that's kind of how we've gone.
So still getting back to the difference with the Upper Tulare Creek versus the other 2, I guess the other thing to look at, and I didn't, but it just occurred to me, so can you see a corresponding increase in groundwater levels at that time that would, so the groundwater hydrographs, have you looked at those, and do they?
I would ask you to hold off till tomorrow to ask, because they're going to cover the whole groundwater modeling exercise then.
Yeah.
And actually, that's a good question.
Just to corroborate that recharge inference, right?
But I suspect that is the case because the groundwater modeling and all the studies, from my understanding, talking to the groundwater guys, is that they're able to reproduce those hydrograph patterns, and that's consistent with their groundwater level measurements. So I would be surprised if that wasn't the case.
Okay. No, I think that's it for me.
Does anyone want to revisit questions from the panel?
I just have another, just to reiterate something that you mentioned during your talk about the number of stations. So there are some crest stage gauges, but then there are other continuous stations. How many of those are out there?
The crest gauge stations are only on the corridor.
Right.
So there's 13 of those on the corridor. And those ones were all operated from 2005 through, or 2004 to 2008 period. Those crest gauges are not operational at the moment. We've now plugged in 3 continuous gauges along that corridor. The corridor wasn't really the focus of most of the hydrology study, I'll be honest. It's now getting more attention as we're moving forward. We need to expand that data set.
So the total number of continuous gauges
on the corridor, or
no, in the mine study.
In the mine study, well, overall, including the corridor, there's 34.
34.
Okay, there's 26 right in the 350 square miles of what we call the mine study area. Those 3 watersheds have 26 altogether.
And do you know what the long-term plan is for operating all 26?
Okay.
Are they going to go for?
I can't answer that, but I can tell you right now that actually, in fact, all 26 are not currently operating because they're so highly correlated. We did a regression modeling exercise 2 or 3 years ago comparing all the sites, and we found that when we had R-squared values across the full range of flows at various stations of like 0.98 or 0.97, we said, why are we operating both stations? So to optimize the operation, we took out various stations, and then what we use is those regression models to to fill in any periods. So we actually have the full, call it record for the 2004 to 2012 period, but some of that record has been synthesized based on the regression models.
Right.
Because there's a very 5 or 6 year overlap where the regression is so incredibly high because the stations are quite close together. We found, well, this station's sort of redundant. We don't really need this one. Let's save our resources and apply it somewhere else. That's what also allowed us to expand, because to be honest, the whole thing started with 13 stations in 2004. And I guess it's my opportunity to give a plug to the group that's been supporting this, is that when I first got asked to get involved with this, which was back in 2004, I heard, okay, a new mine, there's 3 drainages, and they asked me to give them the recommendations of how many stations and where we should put them. And I said, here we go again. Okay, I'm going to ask for 6. I might get 3, 1 on each. And I came out of the first meeting with 13, and I was like, and the client asking me, are you sure you got enough? And I was like, wow, that's more than I've ever had. So we started with 13, and it has grown progressively as we've decided, I think I need to know a little bit more about this area. Or the groundwater studies, they are suggesting we've got an inconsistency here between this and this, so there must be something going on in this area. Let's put 2 more gauges in here that'll help refine this. Right. So that's how it's gone from 13 to 34 over time. So we don't have 34 over that full period.
Right.
But because all the gauges are in such a small area and they're so highly correlated, we can back calculate what the flow's likely would be with reasonable confidence. I mean, very high correlations. So that's kind of how we filled in the set. Yeah.
Okay.
Yeah.
Yeah, thanks, Gene.
Okay.
Anyone else on the panel?
I got a couple more.
Okay.
The orographic effects and the changes of precipitation with elevation and aspect and everything is very interesting.
Yeah.
Out there. The one slide that was put up, showing the maximum amounts near the coast and then dropping off and then coming back. A couple questions on that. It'd be interesting to be able to tie that down a little bit closer to, be more site specific with it. I mean, the rain gauge stations that you have probably isn't quite sufficient. But have you determined? I know you've determined the runoff for each of the small gauges.
Yeah.
I mean, at least the headwaters gauges in each of these and the tribute. Have you plotted that versus elevation to kind of get a runoff, to get a change versus elevation, or maybe segregate it by aspect? I mean, I think you'd have about 12. You could have about 12 data points on such a relationship, and it'd be interesting to see just what the change is based strictly on runoff now, because again, this becomes input and is used in the water balance stuff later. It'd be interesting to see just how that plots up, and if you could segregate it for aspect, that'd be interesting too.
Okay, within the mine across the
within the 3 watersheds that you're dealing with.
We have done that.
You have done. Is it in one of the reports?
No. Okay, we actually have a figure which we're using for helping us with our modeling exercise. We inputted all the I guess we did it with runoff, but we also did it with precip, working backwards from our watershed model. And we inputted all the points into a GIS program and created a contour map of the whole mine study area showing different contours of precip and how it varies throughout.
And that's based upon the runoff estimate, though, or is based upon the
That's back calculating the precip based on the runoff.
Based on runoff, okay.
Okay, so we've got all the runoff at all these points. And, for instance, in that SK119A basin where it has 45 inches of runoff as opposed to, say, 33, but the precip numbers that we're putting in, that actually shows us combined snowpack and precip. We don't actually know how much is blown in there and how much actually falls in there, because we can't separate the two. The wind is so great, and there has been done a whole bunch of snow studies as well and a snow model, and the drifts are dramatically different. There are areas in there that are completely blown bare in the middle of winter. You can stand up there, it's just rock, and you can go a little further over and it's 100 feet deep. There's a drift that just goes forever, and so that's contributing a lot to the hydrology as well. So the redistribution of that precip, and also talking to the snow guys, they say some of it is actually being blown in from outside those 3 drainages, And so you're actually probably getting a net accumulation of snow being blown in from just.
But if there's some blown in, it's also
Some
it's going to be blown out too.
Some is being blown out, but some is being captured because of the topography, right? You know, in terms of some of those little drainages are very steep, and they capture, and you get these drifts blowing. So how much of that is being contributed? I don't know, but it just confounds the whole thing a little bit in terms of trying to figure out what the precip is. So when we develop the map, it shows how much net precip, whether it be from blowing or falling out of, directly out of the sky, is in that watershed to give us. And again, that's based on estimates of, we have to come up with evapotranspiration estimates, because that's also a loss from the system. We've tried to measure evaporation at the site as well with pans, and that's another one of which hasn't been highly successful. I don't know if you've had experience with pans, but they can be very, very challenging themselves. So anyways, that's, so we may be out by an inch or two in the precip, but we're also then maybe out an inch or two in the evap. But in the big picture, that doesn't really bother us that much, because ultimately what we're after is how much water have we got in the system. So if one's out a little bit, it's countered by the other being out a little bit. But the net balance is how much flow, and the flow numbers are what we have the greatest confidence in.
I notice the wind directions are either southeast or northwest for the most part. Is it southeast? What time of year? How's it break down time year-wise?
I'd have to revisit the data sets, but it is a fairly cyclical and predictive pattern. And depending on the station that you look at, of course, it's different, because you end up with different drainage effects based on topography. But the area that is out at the main mineral area primarily does come across I wish I had my wind roses in front of me, from the southeast, I believe, is the predominant direction. And there's a seasonal effect, and I think it is the winter that is the primary driver in that direction, and then the summer there's more of a downflow.
So summer is more from the northwest,
more from the north, northwest.
Okay, that makes sense. And no, I think one last question for you on low flows and on estimating low flows. On the fisheries, people are going to need low flow estimates and stuff like that. Do you have plans to do things like 10-day, 7-year low, or 10-year, 7-day low flow, stuff like that? I mean, how are you going to do that? Can you talk about how that's going to
happen? I mean, ultimately, we have winter measurements that we have an idea of how the flows recede through the wintertime. As we talked about before, we have that's why we've taken these winter measurements, because that's the lowest flow period of the year. Some sites it's going to be really easy because they go dry. So I can give you 100% what the 7-day low flow is. Okay. Others, it's going to be some uncertainty associated with that. Again, we have the data. There's an error band behind any winter measurement, but it is the most extensive winter measurement program I've ever seen in a small area. So, but the low flows do vary quite a bit from site to site. We know that because the groundwater program is changing. So ideally, we'll use the data, but we'll also get whatever we can out of the groundwater models, et cetera, to help us support it. I can't tell you exactly how it is going to play out. I mean, we're not going to use the USGS regression equations. That's all I can tell you.
Well, that's actually what I was kind of wondering.
I mean, we're not going to do that. So those were done as a first stab. And, if you didn't have anything else, that's what you would use to start with. We have a lot more than that, and we're getting more than that. And that was the whole basis for making this huge effort. For people who don't understand, getting winter flow measurements is not an easy task. Okay, you got to get up to there. You've got to get out to the various sites. Half the time, there's some big wind blowing, the choppers can't fly, so you're there forever, not doing anything. Once they finally do get out there, they drop the crew off. It's great. They sling the gear in. You go in. You dig through 6 feet of snow. You get a trench across you find the ice. You get all the ice auger out. You fire it up, zing, zing, and then you blow the blade out, and you spend 2 hours messing with the thing. You finally get the thing all the way across. It's all good. You get in there, and we had to develop little instruments to get all the slush ice out of the holes that we'd augered and all the rest of it. You get the instrument down there, and, sometimes you'd hit nothing. So you'd go, okay, great. We're not even in the right place. And so then you go over and do the whole thing again somewhere else. You finally get all the measurements. We got a site. Storm comes in. Guess what? We're spending the night. We're staying out here. Everybody got their gear. And then you get the ice the cave or whatever, and they've been stranded at site, and they did that. So they do that every month through the winter at all these different locations. So whatever we got is really good. I mean, compared to anything. So that's, I mean, so there and huge efforts being made to get those because we understand the importance of the low flow and the winter measurements. In so many cases, call it Water Survey of Canada, USGS, they don't publish winter flow measurements in the north because they're so hard. They take the gauges out in the fall and they leave them out, and the only hydrograph you get is the part that starts in the spring and it ends in the fall, and the winter is a bit of a mystery. So, you know, we're well ahead of that. So.
Why would you not do dilution tracer measurement under the ice?
We do that as well. We
It
often
seems
do
a
that.
lot easier.
Well, it doesn't always work because we've actually tried that many, many times, and it does work. It's just when we didn't want to use dye because everybody, despite the fact that dye is inert, it's bright pink or red, and everybody panics when you put red into the creek, even though it's inert. So we use salt, and so we're mixing up salt at well below freezing temperatures. You know, and then you have to get the conductivity meter in there and get the baseline, actually measure your solution, and you got to get in the creek and do that. And then you've got to make sure you've got a decent mixing reach so that so when you measure downstream for people, essentially what you're doing is you're taking a salt solution and you're knowing a known amount of salt and what the conductivity is. You're putting it in the creek, and then you're letting all this flow that's coming through mix with it, and as it travels down, then you go downstream and you take a point measurement downstream, and if you measure there what the conductivity is, that tells you what the dilution was required to give you that conductivity, and that dilution tells you the volume of water that was required to give you the dilution. You can work backwards over time because you get a trace of how that concentration changes over time. You can figure out the volume of water over time, voila, discharge. So that's how that works. But the practical challenges of that are quite great, and particularly with salt, you can't tell how well it's mixed, and you sure can't under the ice. And if it all streams into one little corner and runs down, you have a very high concentration that you're measuring with your 1 point, and you're suddenly saying, oh, we didn't have any water at all because it's the same concentration that I dumped in. Or we hit the other side and it all bypassed, and wow, it's massive. So we've got, you know, the New Halen River running under this thing. It doesn't look quite right. So those are the practical constraints to doing that. So we do salt as well, but we often try and do both. So we do salt, and then we go through the owner's task of drilling all the holes, because salt's great. You have one hole up here and one hole down there, and voila. But so we often do it that, and then we'll also go to places where we'll do two, and we'll take, okay, from here to here, and then let's try a different reach just further slightly downstream or further upstream. And so all these things, yeah, but we do that.
Okay. So. That was the short answer.
While you're on the salt, can I ask a quick question about salt? Why don't, since you're not sure that it's mixed, you could at least have 3 holes, center, right bank, and left bank, and check conductivity. Do you do that?
We've done that too.
Okay.
Yeah,
okay.
We've done that. Yeah. So all the tricks have been worked out over the years. Yeah. So, you know, we've done that, and we've at many other sites as well. We have used dye, so I know the advantages of using dye and all the rest of it. But at sites that are particularly sensitive to perception, we use salt, and then we do you know, double conductivity meters, one on either bank, to make sure that we're getting full mixing across the reach and that kind of thing to confirm. Yeah. So.
Thanks.
I have one more question for
sure.
Brad, if that's okay. Yeah. So you're making these measurements, wind speed. I think you said temperature gradients. Are you measuring temperature gradients?
Yeah, there's temperature at both 2 and 10 meters.
And vapor pressure?
No.
No vapor pressure gradients.
We are doing the barometric pressure.
Yeah, okay. The reason I ask is because in many locations, cold climates, waste disposal, you get freeze drying and wind dusting events. And the vapor pressure temperature relationships are pretty important to understand whether you're going to get that, right? So.
Right, and that's probably something that may be added over time as the design materializes. Right now, most of the monitoring effort for the air quality and the meteorological measurements have been carried around EPA permitting process, collecting the data for that modeling effort, and that's not required input or generally used in those modeling exercises.
Well, there may be modeling exercises. I wasn't going to ask this because it would relate to the mine plan, which we don't have, but there may be modeling exercises required to look at atmospheric dispersion of dust from these waste materials. So So I think that sort of input would be necessary to understand the source.
Yeah, the way the EPA permitting process works for those, they use AirMod as the modeling algorithm of choice, and those inputs aren't typically used in that modeling. Part of the reason why we chose this program is because that is the regulatory arm that applies on it, and so we're looking at all the inputs that would be going towards that. Not to say that there might be other inputs that would help refine the algorithm, for sure.
Mm-hmm. Okay.
Tom's question about modeling dust dispersion. Does that fall into anything that you guys are addressing with the climatological data? I mean, would you eventually want to know what dust is being dispersed and how high and how far?
Right, yeah, eventually, we go back to the need for the plan to be able to do those modeling exercises, because right now all we have is 4 or 5 years worth of meteorological data that tell which direction whatever is out there will be going and how it will be dispersing both vertically and horizontally over time and such. As soon as a plan's available, that gives us more information on the footprint of the facility, how much dust might be exposed, the types of vehicles are going to be used, their emissions that are going to come from the exhaust and dust that they generate in the process, if there's power plants or other facilities there, all that would go into that kind of a model. But you can't really do a whole lot at this point, short of using what's the regionally accepted background concentrations and say, okay, this is where it goes when it floats across the area. There's no contribution inputs that we can put in without major speculation.
I know this is a big issue for Red Dog and the Hall Road as well, as dust dispersion and its impacts on the environment. So, yeah.
Well, great. If there's nothing else from the panel, we'll open it up to the audience for questions for Brad and Jamie.